Well, hi everyone. In this video, I'll be explaining the process we followed to solve our problem situation about critically damped oscillations, which are important in real-life systems like vehicle suspension. The main objective was to design an experiment to determine the damping constant of a liquid using a mass spring system and then analyze a critically damped case. We started by researching damping in real systems. Um, well, in real systems, oscillations lose energy over time due to resistive forces like friction or fluid viscosity, and this is called damp motion. One special case is critical damping, where the system returns to equilibrium without oscillating and in the shortest time possible. This is exactly what we want in a shock absorber, and so it was a great real-world application to study. For our experiment in practice 3, we use a vertical mass spring system submerged in oil, and using tracker software, we analyze the motion and measure how the amplitude decayed over time. From this, we extracted the damping coefficient, which we found to be approximately 22.29 kilograms per second, and then we use the following formulas that are showing in the screen. We rearranged this and solve for the critical mass, and that gave us a value of around 0.670 kilograms. That was the mass needed to achieve the critical damping with the damping coefficient and spring constant we calculated. And then in our results, we observed that the system motion resembled a critically damped response. It returned to equilibrium without visible oscillation and in a relatively short time that match our expectations based on theory. However, we also face a few challenges because first, it was hard to adjust the mass exactly to be calculated to the calculated value due to the limited weight increments. Also, the oil's viscosity might have changed slightly during the experiment, especially due to the temperature and because it was used many times for other experiments of other teams. And finally, the tracker analysis introduced some uncertainty in amplitude measurements. Despite these limitations, we were able to validate the concept of critical damping and understand how damping affects motion in engineered systems. This knowledge is directly applicable to designing shock absorbers in cars, where safety and comfort depend on well-tuned damping. Thanks for watching.